This is the pre-lab lecture for Tech 705, which is the separation of acidic and neutral organic compounds using a technique known as solvent extraction. So we want to look at a little background information about the lab, what we're doing. So the idea is that we want to isolate organic compounds from a mixture. We have some sort of set of unknowns we want to purify or isolate. One example of this is the isolation of material from a natural source such as caffeine from tea, and that's one that we've done in a previous lab. We also may have products from synthetic reactions. If somebody's doing drug synthesis, drug analysis, they may have a mixture of compounds, but there's only one that's physiologically reactive, so we have to isolate that compound from the mixture. Extraction is something that is, as we said, used often, as we saw with the caffeine from tea. And the idea in extraction is that we're going to selectively dissolve the wanted compounds, one or more compounds, into some sort of appropriate solvent. The resulting solution is known as the extract. So this is a common technique. We're used to talking about vanilla extract or peppermint extract. It's the same idea. Those compounds have been extracted from a natural source by dissolving them into some sort of solvent. Now, extraction is usually from one liquid to another, although you can have many types of extraction. You can have extract from a solid to a liquid, you can have solid to gas phase. There's a lot of different ways to extract things. How do we decide what solvent to use? Well, the solvents that are used must be immiscible with one another. So remember, in extraction from a liquid to a liquid, you have two liquids involved. If they are miscible with each other, soluble in each other, you're not going to be able to separate the two liquids. You're not going to be able to get a compound to go from one layer to another because there are no layers. So we need immiscible compounds. When carrying out an extraction, it's important to distinguish that technique from the technique known as washing. So we want to look at the difference between those. And, drawing a line there. All right, so in these two figures, you can see extraction versus washing. So in figure 1, you can see that the desired compound, which is represented by the open circles, is in the original layer along with whatever impurities we want to isolate them from. So when we mix our initial layer with another layer, in this case it just happens to be top and bottom. That's another thing we'll have to figure out which layer is where, and we'll talk about that in a minute. But in extraction, what we're looking for is going from the original layer into the new layer. Now, washing is just the opposite. That's where we wash the impurities out of the original layer into the new layer, leaving behind the item that we want. So you need to distinguish whether you're doing extraction or washing. That helps you keep track of what layer you have and which one you're going to need to isolate. So we need to choose an appropriate solvent. What are the criteria that we use for choosing that solvent? Well, first of all, we said we want them to be immiscible, so we want one to be polar and one to be nonpolar. Remember that like dissolves like, and therefore unlike does not dissolve. So we want two things that are not compatible for solubility. For polar, water is a great example of that. Cheap, easy to obtain. Nonpolar, what are some common solvents that we would use? Hydrocarbons are a very common nonpolar solvent. They have a density less than that of water. Ethers are one that are used often, so also with densities less than that of water. So if you're using either of those two nonpolar solvents, keep in mind that that layer is going to be on top. So another good thing to do as you're carrying this out is sort of label where your layers are going to be. If you're using hydrocarbons or ethers, label those on top, water goes on the bottom. Now, we've also used another type of solvent, chlorinated solvents like dichloromethane, and that's the solvent that we used for extracting the caffeine from the tea. In that one, you'll remember that the dichloromethane was the bottom layer, so it has a density greater than that of water. So in that instance, you would have the water on the top layer. So if you're using dichloromethane, that's on the bottom, ethers and hydrocarbons on the top. The other layer will be your water layer. So we're going to start out with things in aqueous solution. We're going to extract into the other layer. It will depend on which solvent that we choose to use as to which layer we're actually going to focus on after the extraction. We already said that like dissolves like. We're going to use that to our advantage to separate these three compounds that we're going to mix together. So when you look at the compounds that you're separating, if you have polar compounds, those are going to be the ionic compounds, the ones that are metal and non-metal. Those will be more soluble in the polar solvent, like dissolves like. Non-polar compounds are going to be more soluble in those non-polar solvents that we had. So that's what we're going to use to our advantage to isolate these compounds. We need to look at the compounds themselves and decide what's going to be in what layer. Now when you start out, all of your compounds are going to be organic compounds that tend to be fairly nonpolar. What we want to do is take one of those nonpolar compounds and convert it to a very polar compound in the form of its ionic salt. And we can do that through a little bit of acid-base chemistry. So now this is getting a little bit ahead of where you are in lecture, but if we look at, remember those functional groups, we had carboxylic acids, organic acids. If we have an organic acid, or if we have a phenol, which is another type of functional group, and we combine that with a base, what we're going to get are water-soluble anions. This is an acid-base reaction. If you remember from general chemistry, acid-base reactions give some sort of metal salt and water, and those metal salts are soluble. So we're going to take advantage of that. If we have an organic acid, we can react it with a base, and we can turn it into an anion, which is highly soluble in an aqueous solution. So here's an example, for instance, of a carboxylic acid. Remember, this is the functional group for carboxylic acid. We're going to react that with a strong base, such as sodium hydroxide, or a weak base, such as sodium bicarbonate. When we do that, we're going to get this right here. So basically what we've done is cleaved through that hydrogen. That has combined with either the OH to form H2O, or with the bicarbonate to form carbonic acid. And then we have this anion right here, which will now be soluble in water. This is just showing the other functional group, the phenol. So this is what a phenol would look like. It's when you have this OH group attached to this aromatic ring. Okay, so you don't need to worry about that quite as much, but we will be using both of these in this lab. You haven't really seen phenols very much, but that's the big distinction between them. Now in this one, notice that it only shows OH, because this is actually a weaker acid. A phenol is acidic, but it's a weaker acidic compound than an organic acid, than a carboxylic acid. So it requires the strong base in order to react. And we end up again with an ion, which is soluble in water, and then where we cleave that hydrogen off, that combines with the hydroxide, and we get a water. Okay, so if I use a strong base, I could convert both of these to a water-soluble compound. If I only use a weak base, if I have these two things together, then the weak base will allow me to separate these two. It would create an anion from the carboxylic acid, but not for the phenol. So we're going to take that and use that to our advantage. Just to let you know, the opposite, we're not using this in the lab, but the opposite works as well. If I have a basic compound, such as an amine, and I combine that with an acid, I also get a water-soluble cation. So here's an example of an amine reacting with acid, just the generic form of acid. Okay, now again, we're not using that in lab, so you don't have to worry so much about that reaction. Focus more on these two at the top. Those are the two that you'll be seeing in the lab. so we're getting into some acid-base chemistry. You'll have to dig back into general chemistry, but know that the anion, let's focus on the case we started first where we formed anions. The anion that is formed is the conjugate base of the original acid. So whatever acid you have, carboxylic acid or phenol, the anion that you form is what is known as the conjugate of that. It's sort of the opposite in terms of a base. Okay, if you start with a cation, such as with the amine, then what is formed is a conjugate acid from that original amine. The stronger the material being reacted, okay, again, we're going to focus on acid. The stronger the acid that's being reacted, the weaker the conjugate base that is formed. And this is just something to start getting you used to looking at the idea of acid strength. That becomes very important in organic chemistry. So just as a reminder to you, we're going to be looking at something known as the pKa. So if you remember talking about pH, which is the hydronium ion potential, well, this is the acid potential of the material. The smaller the number, the stronger the acid. That seems a little counterintuitive. But if we look at this, p-toluic acid is a type of carboxylic acid. It has a pKa of 4.2. Now, when I create the anion and then water, I end up with something with a pKa of 16. So notice that this is a very high pKa, that's a very weak acid. If I look at the reaction with a weak base, okay, I still end up with the same p-toluate anion, but now instead of water, I'm getting this carbonic acid. So if you remember, it makes sense that, you know, water is going to be a weaker acid than carbonic acid, pKa of 6.4. So for these two conjugates, this is the stronger acid. When we started out, you know, these were both the same strength, but now this was the stronger base. Stronger base leads to weaker over here, weaker leads to stronger over here. Now if I look at a phenol, so this one starting out has a pKa of 10.2, so already I can see, compared to the p-toluic acid, that it is a weaker acid. It requires the stronger base to form the anion, and now I have water, which has a very high pKa, so very weak acid strength. Now if I were to take this p-tert-butyl-phenol and try to react it with bicarb, nothing would happen. This is not a strong enough base to react, so these two don't go together. P-tert-butyl-phenol, pKa of 10.2, this one just not strong enough to do that. All right, so here's a flow chart just showing you the order of the lab, what you're going to be doing. So what you're going to do is start with these three organic compounds. You've got acetanilide, p-toluic acid, and p-tert-butyl-phenol. So p-toluic acid is carboxylic acid, so that will be your highest strength. P-tert-butyl-phenol, that is still acidic but weaker than the p-toluic. And then the acetanilide that you used before with the recrystallization is essentially neutral. It doesn't really have an acid strength. Those are the three that we're trying to separate. We're going to start by dissolving them in 5 milliliters of something known as tert-butyl methyl ether. So it's just a good non-polar solvent that will dissolve these organic compounds starting out. So in step number 1, you're going to take and measure out about 50 to 70 milligrams of acetanilide, between 80 and 120 milligrams of the acid, and the same for the phenol. Now again, it doesn't have to be any particular amount, just somewhere in those ranges. You do need to record the exact amount though, because you will be doing percent yield at the end. So measure those out, dissolve them in the 5 milliliters of ether, mix them together, and then what you're going to do is add a sodium bicarb solution. Now, sodium bicarbonate, we said, is a weak base. It's not the strong base. So a weak base is going to be enough to react with the p-toluic, but not with the other two. So at that point, after carrying out the extraction, you will have your ether layer, which will still contain your acetanilide and your phenol. And now what you've done is converted your p-toluic acid into an ion. Notice here, it's not what it was before. It's become an ion, which is water soluble. You have 2 layers and you have different compounds in each one. Okay. Now to do that, it's going to be a half molar solution. You'll use 2 milliliters of that 3 times. So you'll have a total of about 6 milliliters of extract, and then you'll add another milliliter of water at the end just to wash it out and make sure you got everything. So 7 milliliters of this aqueous layer is what you'll have, and then the rest is in the ether layer. All right, now we're going to leave the aqueous layer for a moment. We're going to come back to our ether layer. We still have 2 compounds to separate. We're going to do that now by using a strong base. The strong base will be enough to react with the phenol. It will not react with the acid analyte. So we carry out our extraction. In the ether layer, here's the acid analyte. Nothing happened to that. Okay, and it's the same thing, half molar sodium hydroxide solution, 3 extracts with 2 mils apiece, and then a milliliter of water to wash. So 7 mils again of aqueous solution. Again, it is no longer phenol, it's the ion of the phenol. All right, so now I have all 3 compounds separated. Here's the acid analyte. Here's the phenol in its ionic form, so it's not really phenol. And here is the carboxylic acid, again, in its ion form, not really the acid we're looking for. So I have to do 2 things. One is I have to convert any compound back to its original state if it's not in that original state. The other thing I have to do is clean everything up and get it out of solution. So here's how we're going to do that. We're going to start with the acid right over here. Now, if a base pulled that proton off, okay, we're missing a proton, what we're going to do is plug it back on, and we're going to use an acid to do that. So you're going to use hydrochloric acid, 3 molar, add it dropwise until the pH drops below 3. You'll monitor that with pH paper. When you do that, it will crash out of solution, so you'll have a solid. You'll just use vacuum filtration. The liquid gets discarded, and the residue, you're going to let that dry. That's your carboxylic acid. You'll measure that and record that. All right, now to get your phenol back, same thing, exact same way. You just need to put those protons back on there. 3 molar acid, dropwise until pH drops below 3. Filter it out, discard the residue, and then here's your phenol. You will dry that and measure it out. Now for the ether layer, you've got your acid analyte in there. All you need to do is get the solvent off of there. Now the problem is you may have residual water from these other steps. Some of this aqueous layer might still be in there. So we want to get rid of the water layer first. We're going to dry it using anhydrous sodium sulfate. You're going to put it in, let it clump up like you did before. Now that will stick in the bottom of your centrifuge tube. You won't really need to filter that. What you can do is just carefully pour the ether layer off the top. The solid layer in the bottom, you'll just toss that. You'll have your acid analyte in ether. You're going to put it in the hood on a very low hot plate and just let the solvent evaporate off. The vapor it says discard, that's going out through the hood, and what you have left will be solid acid analyte. Let it cool, weigh that out. Boom, you've got all 3 of your compounds, weigh them out, get your percent yield on them. And then you can see how well the process of separating or extracting these compounds worked. Now be aware when you do this, the method you're going to use is the microscale. You're given a microscale and a semi-microscale. Use the microscale extraction, which I believe the numbers may be different in the book you have. In the book I have, it's pages 104 to 109. Don't worry about page numbers, just find where the microscale extraction is. All right, so just to follow the flow of where these compounds are going, acid analyte stays in the ether layer the whole way. Okay, so there's the progress for ether. If we look at butyric acid, that immediately gets put into the aqueous layer and then gets converted back. The phenol starts out staying in the ether layer, then gets pulled out into the aqueous layer, and then gets recovered. Okay, so that's just showing you the progress of each of these compounds and where those go. You may find it helpful to sort of sketch that out on your flowchart to keep track of where things are. Now there are some common problems that come up in this lab. I just want to talk to you about those and what you do about them if they happen. One problem is that sometimes people get a little bit too enthusiastic when they're mixing their 2 layers together. doing the extraction, and you get what is known as an emulsion that forms between the two layers. So it actually ends up looking like you have three layers. You've got your clear aqueous layer here, you've got this cloudy layer in between, and then you've got this clear ether layer on top. Well, this is an emulsion of the water and the ether right here, and you've got to get that separated. A couple of different ways you can do that. One is just try gently swirling it. Sometimes just that action is enough to break that emulsion apart. If that doesn't work, then what you can do is add a couple of drops of saturated aqueous sodium chloride solution, a couple of drops of ethanol, or some other kind of solvent that just sort of breaks up the surface tension in that emulsion and lets it separate out. If all else fails, if those two things don't work, you really don't want to have to do this, but if you have to, you can filter the mixture, and that emulsion will kind of stick in there and allow you to separate, because you really can't separate at that emulsion. It doesn't form a clear layer. Best way to take care of an emulsion is not to let it form in the first place. Just be careful in your extraction. You want to thoroughly mix, but just don't do it overly enthusiastically. Another problem that can happen is that traces of ether get left in the aqueous solution. That can sometimes keep your product from crystallizing and crashing out. This would be like steps 4 and 5 in your procedure. If that happens, what you need to do is just remove the ether. So gently warm the solution on a hot plate, just not even very hot, just to about 60 degrees Celsius. Let it cool down. That will be enough to evaporate out the ether. That should encourage crystallization. Only do that if you do not get crystallization from your aqueous layers when you acidify. All right, so just a few notes about safety. Do be aware of what you're handling. Acid analyte is toxic. It can also be an irritant to mucous membranes. The phenol is corrosive. The acid is an irritant as well. Methyl ether is flammable and an irritant. Keep it away from flames, any heat source. Sodium hydroxide is toxic and corrosive. Hydrochloric acid is toxic. Also be aware when you mix that into the layer with the sodium bicarbonate, it does form CO2 and it tends to foam up. So add it very slowly and carefully. Give it a chance to finish foaming before you add any more so it doesn't foam up and out of the container. And the anhydrous sodium sulfate is what is known as hygroscopic. So if you're not familiar with that term, it means that it absorbs water from its surroundings. That's the whole point of it, is we're using it to dry any water out of our solution. The problem is it dries water out of anything it touches. If it lands on the counter, it absorbs moisture out of the air, it turns into a puddle, which is then a corrosive puddle. It will damage your skin if you touch it. If you happen to get it on your skin, guess what? It pulls the moisture right out of your skin. So it acts very much as an irritant in that way. So just handle that carefully. When you're finished, you transfer all the waste to any appropriately labeled containers. Be sure to wash down the bench top, wash your hands thoroughly before you leave. Make sure there's no traces of any of these compounds on you before you go.